Hi, this is Justin Fowler. We're going to talk about the fate of lactate. So some learning objectives very quickly. We want to review ATP and the energy systems, which is going to help us to define lactate and describe how lactate, lactic acid differ, as well as the consequences of lactate accumulation on our abilities to sustain exercise. There's also some other learning objectives listed here. But please feel free to go through those at your convenience. Let's get started. So ATP, adenosine triphosphate, is a high energy molecule, and it's found in every cell, often referred to as the energy currency of life. Energy from the oxidation of macronutrients, proteins, to a limited degree, carbohydrates, and fat. They're harvested and funneled through the energy-rich compound ATP, which is then utilized to power bodily functions like muscle contraction. According to McCardle Catch and Catch, the body always attempts to maintain a continuous supply of ATP through the following metabolic pathways listed below. You can see that we correlated pictures to each pathway. So matches with the ATP PCR system. Energy is immediately available, but it burns out fast. And the reason that it's immediately available, but also burns out fast, is because it comes from intramuscular sources. It's also anaerobic and lasts approximately 1 to 30 seconds. Then energy from ATP resynthesis must come from stored macronutrients. So as we ladder match, place it into the fire pit, we have our group of papers there. There's a smooth transition of energy. This transfer with the glycolytic anaerobic system in the group of papers, understand that glycolytic anaerobic system is also readily available, but it burns out fairly quickly as well. It's anaerobic as well and lasts for approximately 30 seconds to 3 minutes. So we want to take our firewood there then and then place it on top. And as we do so, that's representing the oxidative system or oxidative phosphorylation. It's vital to remember that the oxidative system obviously requires oxygen. So it's going to take longer to make into usable energy, just like it's going to take longer to get our firewood burning, but it's going to burn for a much longer or extended period to provide energy for extended bouts of exercise. Let's take this information then and utilize it in our discussion about lactate. So lactate and lactic acid are commonly believed by many to be the same substances, but they're not. And according to McCardle Catch and Catch, lactic acid and lactate are different. They're different substances. Lactate is a byproduct of lactic acid. Lactic acid, which is formed during anaerobic glycolysis, it breaks apart and releases a hydrogen ion. And the remaining compounds bind with a positively charged sodium or potassium ion to form lactate. So what do we do then when we have an accumulation of lactate? Well, the production of NADH, what happens is it exceeds the muscle cell's ability to shuttle hydrogens through the respiratory chain because of insufficient oxygen supply. So the hydrogens begin to kind of like butt up against one another or build up against one another. But according to McCardle Catch and Catch, blood lactate does not accumulate during all levels of physical activity. During our lighter to moderate activity at 50% or less of aerobic capacity, lactate oxidation equals lactate production, so it's smooth coming in and smooth going out. Additionally, McCardle Catch and Catch described that for healthy untrained persons, blood lactate begins to accumulate and rise at about 50 to 55% of maximal capacity for aerobic metabolism, and we can see that in the diagram here below. And we see the yellow line representing an untrained individual and the red dashed line a trained individual. We can see an increase in blood lactate concentration from light, moderate to strenuous exercise, and corresponding increases in percentage VO2 max. We see that blood lactate threshold for the untrained person is right at 50 to 55% of maximal capacity. But we see with the trained individual, it's roughly around 75, so there's an improvement there through training. Some other key items associated with lactate concentration and or lactate threshold is the intensity of the exercise, the duration of the exercise, and the training level, obviously, we just talked about, of the individual performing the exercise. Let's take that information in and talk about how the presence of oxygen influences our lactic pathways. So as you remember, we went over our ATP production from a glucose molecule is a 6-carbon molecule, which went through glycolysis, and we had a 2 ATP net gain, which all of this was occurring in the cytoplasm without oxygen. Through glycolysis, we also had 2 NADH and 2 3-carbon pyruvates produced. When oxygen was present or available, we went through oxidation and all the way through the Krebs cycle to the electron transport chain. But if the energy requirements are immediate and intense, then we have to go a faster route. So let's look at oxygen's influence here on lactic pathways and the difference between fast versus slow glycolysis. So we do so in looking at the picture to the right. We have athletes running the 400 meters in the Olympics, and the 400 meters is a very intense race where essentially you're running full speed for 400 full meters. And out of this we have, again, our hydrogen being created. Well, we go back to our glucose. So our glucose, the 6-carbon molecule, which had netted us 2 ATP, was split into 2 3-carbon pyruvates. But the demands for the activity were so high and immediate need for energy so high, we do not have time to go through slow glycolysis because that requires 60 to 80 seconds to resynthesize ATP for energy. So the pyruvates got to find essentially a different path or route, and it does so by finding one of the hydrogens and through a process of lactate dehydrogenase attaches there and becomes a lactate. So the lactate itself is not it's not our problem. It actually is helping us because it is buffering us, or buffering from us becoming acidic. It's also acting as a fuel, as hydrogen can then be stripped back off to form pyruvate, which we can talk about in just a second. And it is also a hormone and can signal tissues in the body what's going on. So we have to go through fast glycolysis because of the intensity and energy needs. This leads us to the Cori cycle. So we have, once again, on the left-hand side, within the cytoplasm, our glucose, the 6-carbon molecule, goes through glycolysis, which we've discussed. We have our 2 pyruvate created, and now our 2 lactate. Our 2 lactate can then go through the blood stream into the liver, and the process essentially reverses. So our lactate will then become 2 pyruvate through glycogenesis into 2 glucose, back through the bloodstream and into the muscles. So we have this cycle or circle. We notice also that within the liver, through this process, we lose 6 ATP. And this happens fairly quickly, but in a limited amount. So how are the pathways affected by exercise intensity, OBLA, and training adaptations? So a decrease in exercise intensity results in a reduced rate of lactate formation, obviously during physical activity. Also a decrease in exercise intensity then allows for lactate clearance to keep pace with lactate formation. So again, we have smooth coming in and smooth going out based on intensity. However, an increase in intensity increases lactate formation and makes the blood pH more difficult to manage. And according to McCardle, Catch and Catch, OBLA begins to signify when blood lactate concentration systematically increases to 4 millimoles. OBLA kicks in once the lactate threshold is reached, while the intensity and duration of exercise continues. So it provides us a little bit of a boost here at the end, and we can see that in the diagram or pictured here in the middle of the page. We have onset blood lactate concentration. So again, we see the yellow line is the untrained individual, the red line is the trained individual, and we see that for the untrained lactate threshold, it's right again at about 50. The trained lactate threshold was at about 70 to 75, but OBLA allows for it to continue a little bit longer or provide some form of a boost. Also important to mention that an accumulation of lactate can change the blood pH, and as it does so, and we continue to have blood lactate concentration increase, we have a resulting muscle fatigue. But training adaptations can help in this. So training adaptations for endurance athletes, some of those adaptations include favorable aerobic responses. Training adaptations also allow sprint and power athletes to achieve 20 to 30% higher blood lactate levels. So the training is going to help us with our fatigue and aerobic responses, as well as higher blood lactate levels. So I hope you enjoyed the presentation and answered any and all of your questions. If you have anything to ask or comments, please feel free to let me know, and have a great day.